Hello, my name is Maria Fernandez, Energy Efficiency Engineer from the National Renewable Energy Center of Spain and coordinator of the ePANACEA project. The main project objective is the development of an energy assessment methodology for buildings that allow overcoming current EPC challenges, such as the performance gap. Within the project context, three energy assessment methods are being developed at the moment. The whole ePANACEA methodology will be integrated on an online platform so-called SEPAP. However, specifically, the assessment method 3, based on dynamic and calibrated simulations, will require the support from a local tool developed with this purpose. This local tool is called SEPAP Tool, and the main objective of this video recording is to give you a brief tour through the SEPAP Tool workflow and their main functionalities. For that, I'm going to follow these points. First, the context of the software development. Secondly, a brief overview through the list of functionalities. Then, a tool tour through the development of a case study. After a manual, we will develop a manual calibration based on monitoring data from smart meters. And finally, I would like to develop an assessment of an energy efficiency measure based on a PV installation and on the building roof. Well, regarding the context of the software, the assessment method 3 of the ePANACEA methodology uses Energy Plus as simulation engine for developing the EPV assessment. OpenStudio is a more user-friendly tool than working directly with Energy Plus objects that require of advanced knowledge and a great effort to implement detailed HVAC systems. So OpenStudio was received as a good evolution by all of us that were using Energy Plus from the very beginning. However, OpenStudio still has some difficulties on which we have worked through the development of the SEPAP tool that uses all the best of Energy Plus and OpenStudio, but implements several improvements in terms of user-friendliness, since it incorporates some functionalities or templates for introduction of the space definition, materials, construction sets, thermal bridges, schedules, HVAC systems, and renewable energy sources. Okay, then this is how the graphical interface looks like, since SketchUp can be used for building modeling. The SEPAP tool can, as you see, SEPAP tool can be found through the extension section here. And we can see the list of functionalities that are included. As you can see, you can select the SEPAP tool plugin, and this is the list of main functionalities that can conduct to additional functionalities under each section. We can define here a new project, define the building type, introduce some administrative data. Here we can introduce construction systems through material definition, glass definition, define of construction system. Here as our construction system with heat internal source. And finally, we can define a construction set composed by several constructions. The space definition include a classification between if the space is contributing to the reference size or the space is not contributing to the reference size, as the international standards recommend. Here we can introduce thermal bridges into our model, for example, for facade pillars, corners, window perimeters, and so on. Here, there is the functionality that incorporate templates, default templates for the introduction of HVAC system. We can introduce here the domestic hot water. Then we can select the spaces that are going to be supplied by heating for one of these systems. We can introduce electric baseboard heaters, electric radiant floor, central boiler and baseboards, individual boiler and baseboards, central boiler and heating radiant floors, individual boiler and heating radiant floors, individual heat pumps, and individual heat pumps plus baseboards. This is regarding the heating or heating and cooling systems. Here we find the functionality of introduce a PV system that we are going to try at the end of this session. And this is the functionality to remove the PV system if you need it. Then here the same for introducing an installation of solar thermal collectors. Here is the template for the introduction of an air loop with heat recovery for the ventilation system, and finally the functionality of removing all systems if it is required. In this section, other tools, we can find several tools to develop quick models. For example, in the section of Windows, Windows to introduce Windows to wall ratio, introduce window frames, overhangs, etc. For walls, we can define here if we need to make some walls adiabatic, for example. Some organization issues regarding async floors, renaming surfaces, and so on. And here is a functionality to create file structure if it is missing. When we have introduced the whole model, we have the possibility to go to the run section that allow us to move directly to OpenStudio and run the simulation. We have also added the functionality of develop a sensitivity analysis since the objective of the SEPAP tool is to provide support for the development of the assessment method 3. We will need the development of this sensitivity analysis with the purpose of develop the calibration of the model. And finally, here there are some functionalities related to problem solving, since maybe we have some surfaces or some elements that are being introducing some problems into the simulation, and we need to remove them quickly. Then we are going to proceed to an example. Here we have the case study, a case study already developed. This is an individual dwelling, an apartment, part of a bigger apartment, a multifamily block. This is model. This has been a model with these thermal zones. 1, 2, 3, 4, 5, 6, 7, 8 thermal zones representing bathrooms, 3 bedrooms, the corridor, kitchen, living room, and stairs. We are going to, we have also introduced here the remote settings corresponding to closed buildings. And we are going to try to develop this model quickly, but with some simplification. We are going to start from the beginning, and we are going to model the same apartment with just 3 thermal zones. One for the S orientation, one for west orientation, and the third one for an internal zone. We're going to proceed with that. Okay, as I have mentioned, I'm going to proceed with a new model from the beginning, trying to develop a very simplified version of the previous one, no? Of this dwelling part of a multi-family block. So we are going to start with the first step of the SEPAP tool, creating a new project. So we need to call here the name of the new folder. In this case, would be a sample, and the name of the file name I'm going to maintain new project. Okay, now a new project has been created, and I'm going to go to the second step, define building type. In this window, we have to define which weather data we are going to, or which climate we are going to use for the simulation. In this case, we are in Spain, in Pamplona, and we can use synthetic data for a regular year, weather data for a regular year, or use actual data in order to calibrate the model with actual operational conditions. We are going to use actual data for the year 2020 in this case. We are going to adjust a little bit this to 0.4 for the air change per hour. This is the renovation with outdoors air inside the dwelling, and this is the air permeability of windows. We are going to maintain this value. So next would be administrative data, but we are going to skip this step because it's not relevant for this case. Next step would be the definition of construction systems. For do that, we need to define material definitions. Material definition, although the SEPAP tool integrate a very complete database of materials. If you need to define a particular material for your project, you only have to select this window, define here the characteristics, the thermal characteristics of this new material with name, thickness, conductivity, density, and so on. Then click on save and exit, and you will have there a new material saved in the database. After you have defined the materials, you need to define the construction set. I am not going to do that at the moment because this is a very laborious process in which you need to name each construction system in the building for this model. Put each layer here, and after you can get these global values, thermal characteristics for transmittance, resistance, and so on. In this case, I am going to use the construction system, the default construction system that are integrated on the SEPAP. However, we would need to use this section of the SEPAP tool in order to define it one by one, each construction system for our model. When we have define all these construction system, we can define a construction set for our model. That means to define a list of construction systems for walls, floors, roof, exterior or interior, and so on. We only have to specify which construction systems have to put here. No, for example, we open this folder, and we can move its system to its construction system to its part of element of the envelope. In this case, we are going to skip from this step also, but it's very easy to complete. Only you need time, no? But it's not difficult to develop this step. In this case, we are going to use the default construction set and the default construction system in order to develop the model faster. Okay, then I'm going to define the geometry. The geometry we are going to define through 3 thermal zones. We are going to start here with the first space. We are going to draw here 6. Oh, sorry. No, I'm going to start drawing this. Okay. As you can see, it's very easy because you can use all the functionalities of SketchUp to do that. The only issue is you need to define each box for the space before drawing any thermal zone. So here we are going to draw the interior zone. Well, when we have draw the 3 spaces or thermal zones, we can then edit a little bit the envelope. In this case, we need to draw windows in the facades of west and east orientations. We can choose to draw windows using a wall ratio, for example, 20% ratio, for example, in this case, using this functionality, windows to wall ratio, and we can choose window to wall ratio fraction. In this case, we are going to use 25% and offset meter from the floor, pues, so 0.8. So the window is drawn here. Or we can choose to draw windows one by one according to the specific size of each window. As you can see, this is a very, very simplified model than of the previous one, no, I show you here. This is similar, the orientation is similar, S-West, the dimension is similar, but we have simplified a number of thermal zones with the aim to develop the model faster. But at the end, we will come back to this model to see the results. So when we already define windows in the model, we need to define also the characteristics of the thermal envelope. If we select the render by boundary condition button, we can see that at the moment the floor is in contact with the ground and all the envelope highlighted in blue color is in contact with outdoors. So now we should define each surface that should be adiabatic. No, for example, all this side will be adiabatic, all this side will be adiabatic. We can do that with 2 options. We can select, for example, use this filter and use a class of surface, in this case surface, and type roof ceiling, and we search in the whole model, and then we can select this function about walls and make adiabatic in this window, dialog window. We are asked to select the construction for the new adiabatic surface. We need to choose a construction system then from this list. We are going to select this one as an example. Then we can save, and we can open the file again to see the whole geometry, and you can see that now these surfaces are highlighted in pink color. That means that are adiabatic. Another issue important to define properly the model is the heat exchange between different thermal zones or spaces. In this case, this interior partition is not, these interior partitions aren't adiabatic, so we need to specify in the model that. In this case, it's easy to select another function regarding this and use for the walls surface matching. That means intersect before matching. This is good to say yes, because if we have different geometries, the tool will do what is necessary to match properly the surfaces. And then when you use this type of visualization, because you need to select the zones before do that. So I make this again. Okay. And you can see that these surfaces now are highlighted in green color. So green color means that heat transfer between these zones exist. Okay, if we open now the more detailed model and we choose the same visualization mode, we can see how the different parts of the building envelope was defined or classified according to this color criteria. No, you can see that only the surfaces that are in contact with outdoors are highlighted in blue color. The rest of surfaces are highlighted in pink color. That means all these are adiabatic. And if we choose the transparent mode, we can see again that all interior partitions are highlighted in green color. That means that heat transfer can exist between different thermal zones in the model. Okay. If we continue with the next step defined in the list of the SEPAP tool functionalities, we find the space definition. In this case, we can choose between a space contributing to the reference size or a space not contributing to the reference size. In this case, the three spaces are thermal zones, condition spaces, so the three zones will be a space contributing to the reference size. We need to select the three spaces and then choose this option. In this case, we have to choose which is the space type. The space type is associated to certain schedules and operational conditions. So in this case, it's a dwelling. So we are going to choose a space category residential living space according to the standard 52,000. This dwelling only have a heating system, so we are going to choose that. And the construction set, we are going to choose as a default set of construction systems would be ventilated facade with insulating glass, for example. Space height we are going to define is 2 meters and 4 centimeters, and the light power system by default would be 4 watts per square meter for sample. So in this case, we have already defined the spaces type, the space type. In this case, next step would be the definition of thermal breaches. As an example, I'm going to choose, for example, facing a slab thermal breach. It's important to mention that we can choose to model thermal breaches through this way. That means define the linear transmittance, the length of each thermal breach, and the SEPAP tool will draw an equivalent surface to represent the thermal losses regarding this issue. Or another way could be to use an equivalent or global thermal transmittance of the envelope where the thermal breaches are integrated. So if we choose this way to define more detailed thermal breaches through equivalent surfaces, we need to choose if we are going to use default values, user value, or values from the catalog the SEPAP tool include. In this case, we are going to use this catalog. For example, if we don't have continuity of insulation, if the dimensional criterion is inside, and this is the slab thicknesses and the U value of the wall. Okay. Then first we need to select the zones to which we need to apply the thermal breaches. In this case, we are going to select these exterior zones, space 1 and space 3, that correspond to S facade and west facade. It is good that we review or know a little bit the length of thermal breaches before its definition. For example, for the facing slab, we know that the dimension should be 6 meters in this case. So we are going to select both zones, going to the functionality related to thermal breaches, facing slab, define the catalog value, discontinuity in the wall insulation, inside dimensional criterion. We are going to modify a little bit the value of the thermal transmittance of the envelope. The slab thicknesses, yes, we can estimate that it's 30 centimeters, and we are going to review here the length of the thermal breach to 6 meters, because we know that only this dimension is outside, is in contact with outdoors conditions. So we apply this thermal breach and okay. Then we see how these additional surfaces appears in our model. That means that this additional surface represent the thermal losses of each zone with the exterior due to this thermal breach. Once we have the model defined with its geometry, thermal envelope, space type definition, and so on, including thermal breaches with additional equivalent surfaces or integrated in the current thermal envelope, we can move to the next step in the methodology. That would be the introduction of the HVAC systems. First of all, we need to define the domestic hot water definition. I have already prepared this for this particular case. For this dwelling and the Spanish regulation, 84 liters per day at 60 Celsius degrees are considered enough to cover the daily domestic hot water needs. And I'm going to select at the moment electricity as a fuel for the generation of this hot water with a thermal efficiency of 95%, and I'm going to maintain these default values for the tank volume and the heat loss coefficient of this tank. However, I am going to show you how we can change this with a very little effort from the OpenStudio section. When we have already introduced this system, we can already go to run the simulation. In this case, the SEPAP tool open directly OpenStudio, where we are going to manage the simulation. We wait for a second, and then here is OpenStudio. We have a lot of information here related to all the model information we have introduced through the graphical interface. In this case, I would like to show you the domestic hot water installation that we have just introduced. In this case, we have defined a first tentative installation. This is the water plant loop to cover the domestic hot water needs, but in this case, this particular dwelling don't have this electric tank for generation, but instead this supply is covered by a district heating. So it's very easy to go to these library objects of Energy Plus, go to the object of district heating, and just moving the object to this current water plant loop and deleting the previous one, we already have the plant loop to cover this domestic hot water. Then we can indeed run the simulation. First, we are going to select the variable district heating hot water rate in order to see the energy that we need to provide for the generation of this domestic hot water needs. Now we can run the simulation. Remember that we are managing a dynamic simulation. That means that the programs need to evaluate the whole year with 8,760 hours. And when the running is finished, we can go to the results summary sections and open the results hourly. For example, here, if we select the variable district heating hot water rate, we can see that it is the energy need through the whole year for cover energy needs for domestic hot water. So we are going now to move to the rest of the HVAC system. Okay, now to see how the HVAC definition for the heating system, we are going to move to this more detailed model to see something a little bit more complicated. This model includes just the geometry, the thermal envelope, and the space definition as we have seen with the simplified model. I have already included the domestic hot water installation in the same way that we have seen previously. And now we're going to move then to the next step, that is the definition of the HVAC for heating. In this case, I'm going to choose one of the default templates included in the SEPAP tool. I'm going to choose central boiler and baseboards. That means we need to select first the spaces for the definition. Don't forget this because it's very important. I'm going to select the condition zones first, all the thermal zones included in the dwelling, 2 bedrooms, 3 bedrooms, corridor, kitchen, and living room. Then we go to the SEPAP tool extension, go to HVAC definition, and select the central boiler and baseboard to generate a hot water plant loop with this installation. We need to fill this information first. The boiler type, I'm going to select standard at the moment, fuel gas, natural gas. Outlet temperature for the loop is 80 degrees, thermal efficiency 85%, and remove current zone HVAC system. We can choose true or false. In this case, there are not any other HVAC at zone level, so it's not relevant in this case. Okay. Then we can save our model just in case, and we can go again to the run section that directly open Studio where we can edit a little bit the default templates that the SEPAP tool provides. Once we open the Open Studio interface, we can go again to the HVAC system section and select the heating hot water loop. This is the water plant loop that we have just created with the default template provided by the SEPAP tool. This is a plant loop with a pump, a standard boiler, pipes, and one baseboard or radiator per thermal zone for providing heating. In this case, this dwelling is supplied by a district heating, not by an individual standard boiler. So we are going to change again the heating, the generator, deleting the standard boiler and replacing it by a district heating. We need to search here in library the district heating section and move here and delete the standard boiler. Now the HVAC plant for the heating system would be. Now, before running the simulation, I would like to comment some aspects related to operational conditions and internal loads. You can find here in the sections of schedule sets, schedules, and loads. These aspects are defined automatically by the SEPAP tool when we define the space types, implementing standard schedules that you can find here. These aspects represent the building users' behaviors related to the energy use, which can imply high deviations between actual and theoretical consumption patterns, contributing to the well-known performance gap. This is the reason why the ePANACEA project is working on the integration of actual building energy use data, including, besides actual weather data, actual schedules and peak loads derived from the post-processing of smart meters data. For this particular case, I have already uploaded actual building data for electric equipment, lighting, and thermostat set points in order to obtain a pre-calibrated model that provides accurate results and can be used for accurate assessment of energy efficiency measures implementations. I have developed this schedule set for this particular case, where I have included an occupancy schedule, a lighting schedule, and electric equipment schedule. These schedules have been uploaded from external files derived from post-processing of these smart meters. According also to data monitoring with available smart meters, I have also include actual peak loads for lighting. For example, in this case, we have include 10.9 watt per square meter for lighting system. And for electric equipment, we have identified a value of 27.2 watt per square meter. So with these actual peak loads and schedules, we are going to run the simulations. Also, we can check here in the schedule section the thermostats that we are using for the actual performance. In this case, I have defined this schedule, residential heating set point, for the Spanish case 3. In this case is the name of this case study. And we can find here that we have during the winter session we have set 22 Celsius degree between more or less 5 and 10 p.m. as you can see here in the functionality for defined schedules in OpenStudio. Then with all this information regarding the actual performance of this dwelling, we are going to run the simulation. When the simulation is completed, we can check the results through the results summary section. We have already included here an option of reporting of OpenStudio that allow us to check at a glance an overview of the energy use in our model. We can check here several tables regarding unmet hours, for example, the hours that are not meeting the set point of the thermostat, an overview regarding here the energy use, the percentage for heating, interior lighting, and interior equipment. This, the disaggregation by energy fuel between electricity and district heating in this case, the distribution for the electricity between electric equipment in gray color and lighting in yellow. We can see here the distribution of energy use by month. You can see the distribution between lighting and electric equipment through the whole year. Here you can see the distribution of energy use related to the district heating. This district heating includes the energy use for heating as well as for domestic hot water. And this is the distribution. This is the electricity peak demand for each month in kilowatts. The district heating peak demand in kilowatts for the district, well, for each month, etc. No, you can see here a lot of information regarding each specific section of the building, for the building envelope, for the building system, for the building energy need, energy use, for the HVAC system, etc. Besides this aggregated data that is very relevant, no, to try to identify the the areas of the energy use in the model that we can improve through the suggestion of some energy efficiency measures, we can go also to the visualization through the, the data viewer that allow us to check all this data in an hourly with an hourly frequency. No, we can see, for example, here the use of district heating, but in orange color you can see the distribution, the hourly energy demand from the district heating for heating purpose, for increase the temperature in the thermal zones until that set point of 22 Celsius degrees. And in blue color you can see the energy demand for cover the domestic hot water needs. This is regarding the district heating use, and we can also check the use of electricity for the lighting system the for each of one for each thermal zone. We can see the use of electricity hourly. For example, we can compare a bedroom versus the living room, no? That would be different size or different amount of electricity due to a different size, no? For these rooms. And we can also check the same for electricity, for electric equipment, for example, no? Then we have a very accurate model with all the spaces, uses, schedules, peak loads, and that distribution along a year, with a very good level of accuracy. Then now we can propose, for example, a measure based on the installation of a PV roof that can compensate this electricity consumption. Besides the information or data related to the energy use for electric equipment, lighting, heating system, and domestic hot water system, other relevant data that we can check through the data viewer are all data related to the indoor environmental quality. For example, zone air temperature or zone air relative humidity, in order to ensure that these requirements are meeting in our model. For example, for the same zone, the bathroom, or the living room, we can check how the set point thermostat is meeting during the winter season. No, we can check as yeah, the thermostat is follow perfectly at 22 degrees. We can also check which is the thermal power required to meet this set point. No, if we check the same zones for the bedroom one for the living room, we can check no the zone heating rate required for follow this set point. Well, finally, to finish this session, we are going to develop the assessment of an energy efficiency measure based on a PV installation on the building roof. For that, we are going to start uh, with the estimation of the building roof associated to this individual model. For that, this is the third floor. As this is the third floor of a multifamily block, we are going to locate the roof 6 meters over our model here. Then we are going to include a PV installation of around 1.2 kilowatt. For that, we estimate more or less 6 square meters. To develop, to include this PV system, we need to draw first a shading element with this functionality, new shading surface group. So we can locate here and we are going to estimate 6 square meters. So, okay. Okay, and we have reverse faces. Okay, the shading has to be in front of the solar radiation like this. Now we are going to well, we are going to rotate the shade to optimize the captation of the panel. So we are going to use a better orientation according to Spain. Okay, I'm trying to this. I'm going to delete this because it is not necessary anymore. Okay, now we go inside this box and rotate this appropriately. Okay, now we already have a set appropriate in orientation to try to maximize the solar radiation and the electricity generation. Now we need to define the PV installation in our Energy Plus model. For that, we have a functionality in the SEPAP tool that makes that much more easy. So we go here to the PV system. We select a new distribution center. We choose the fraction of included surface area with PV cells in this setting that we have just drawn. So we are going to estimate that 90% of the area covered by PV cells. We are going to use a high efficiency PV solar panel. So we are going to include a cell efficiency of 21%, and we are going to include an inverter efficiency of 95%. So we press OK button and it is done. So if we save and open again our model, we can see that our PV installation is there. So now we can proceed with running the simulation in order to check the production, the electricity production of our installation. Well, when we have open Open Studio, the first step to check the PV installation would be to go to the variables, output variables section, and select an appropriate variable to check the electricity production. This is inverter AC output electric power. We have to ensure that this variable is on in order to check the result. Then we only have to run the model again and wait. Then when the simulation is completed again, we can go to the results section, open hourly result. When the data viewer is open, we can go to the variable inverter AC output electric power, and then we can see here the electricity production along the year. Then we can export, in this case export all electricity consumption, for example lighting in this case, and electric power. Can select all these outputs to compare them with the electricity production produced by the PV installation. We can send this data to an Excel sheet, and we can post-process this. Well, then after post-processing data from the calibrated model with actual energy use patterns, we can compare hourly electricity demand with hourly on-site electricity production from the photovoltaic installation. First, these are aggregated monthly data for on-site electricity production in dark green color, and total electricity use inside the dwelling in the light green color. We can see that for the PV installation considered, only there are some excess during the summer months here. However, the global balance is not the only issue. It is important that the assessment also considers hourly data in order to develop accurate economic assessment. Then, if we check a couple of days as representatives, we can see that already in April, during the central day hours here, there will be an electricity excess. On the other hand, for the winter season, it will be more difficult to cover all electricity use at any daytime, as you can see in this graph comparing the PV generation in blue color and in the electricity demand in red color. So, analyzing all this hourly data, we can conclude that the electricity use inside the dwelling will come from the grid in 1,852 kilowatt hours, and 800 kilowatt hour will come from the on-site generation, and around 1,000 kilowatt hour will be exported to the grid. In terms of percentage, this means that the 70% of the electricity use continue coming from the grid. In other words, only the 46% of the on-site electricity will be used in the dwelling, and the rest 54% will be exported to the grid. So all this accurate and disaggregated data give us the opportunity to develop economic assessment according to electricity market prices and propose other strategies, such as, for example, electricity storage, to try to optimize the profitability of the investment, contributing at the same time to the decarbonization of the electricity mix. Well, finally, thank you so much for watching. For more information, I invite you to visit our project website at ePANACEA.eu. We also encourage you to subscribe to our newsletter and follow us on our social networks in order to remain updated on recent developments. You may also choose to contact me directly via email. Thank you so much for your attention.